We were just introduced to the definition of current and circuits and circuit elements like resistors, batteries, and in chapter 24, capacitors. So we're going to combine all these items together and look at some ways to analyze circuits and problem-solving methods to solve circuit problems in this chapter. So this is a cute picture of a circuit I thought was funny. It can kind of look like that. They can get really complicated and really complex. We're not going to deal with anything nearly that crazy, but it may feel that way. So what we're going to do is look at some general methods for analyzing complex networks of resistors, batteries, and capacitors. So the first thing we need to review is what happens when you have multiple resistors in a circuit. And in the same way, we're going to analyze the two different ways that you can connect objects with, a kind of a bipolar arrangement, right? Meaning they have two branches. So remember, capacitors also had two arms or branches or hands, if you will, right? A positive side and a negative side. Well, resistors do too. And so we can connect them either in series or in parallel. And so the first thing we're going to discuss is resistors in series. So when you have resistors in series, they're connected one after the other so that the left hand, if you will, is connected to the right hand. Okay, that's what one after the other means. You could also compare it to maybe the positive side touching the battery to the negative side of the battery. Okay, so that's a series connection. And so differently than capacitors in series, where you added the inverse and then inverse that to get the equivalent capacitance, resistors in series, you actually add straight together. Okay, so the equivalent resistor, which is just a simpler model of multiple resistors, right, in series, the equivalent resistance is equal to R1 plus R2 plus R3, all right? Now resistors in parallel, they're going to behave like capacitors in series. So resistors in parallel, right, let's review what parallel connection means. Parallel connection means that the positive sides are all connected together, the negative sides are all connected together at a junction. So we're going to call point A and point B junctions, okay? And so they're all connected at a junction. And when you have resistors in parallel, you add their resistances in inverse and then inverse that result to get our EQ, our equivalent, okay? And so let's talk about some properties of current and voltage in a resistor. So current in resistors in series and parallel. So current is constant in series resistors. Okay, what that means is the current through R1 is going to equal the current through R2, which will be the same as the current through R3 and the current through the equivalent resistor. Okay, the current value is the same throughout any resistors in series. Okay, now the voltages across each resistor add to the total voltage. Sorry if you can hear my child and dogs in the background. Total voltage. Okay, so the voltage across R1 plus the voltage across R2 plus the voltage across R3 will equal the voltage across that equivalent resistor R1, 2, 3. Okay, they'll add up to that. Resistors in parallel. So resistors in parallel, the potential difference or the voltage between the terminals are equal to each other. Okay, so in other words, for resistors in parallel, the voltage across resistor 1 is equal to the voltage across resistor 2, which is equal to the voltage across resistor 3, which is equal to the voltage across that equivalent resistor. Okay? Current, however, the current entering, although you can see here in this picture, right? The current entering junction A is going to be equal to the same current leaving junction B, but inside that, in that parallel arrangement, that current I is going to split up into 3 different currents, okay? I1, I2, and I3. So current through each resistor is not equal, but they add up to the current through the equivalent resistance. So for resistors in parallel, I1 plus I2 plus I3 will equal I equivalent, okay? And so how do we find each individual current through R1, R2, and R3 since they're not equal? We can apply Ohm's law, all right? So the current, since the voltages are all the same, the current through I1 will equal that voltage. I'm not going to put a subscript because it's the same for a 1, 2, 3 and equivalent over R1, right? That's just using Ohm's law, V equals IR. So the current through resistor 2 will equal the voltage across R1 or R2 or R3 or R equivalent over R2. And then finally, we can find the current through R3 as the voltage across the equivalent resistor, or the voltage across R3 or R2 or R1, whichever one you know, over R3. Okay, so those are the rules, right? So now we have a set of rules, just as we did before for capacitors, but now they're slightly different for resistors. And these are the rules that we're going to use to solve these complex circuits. So let's kind of put those rules to use. So in this example, we have a battery with no internal resistance, a EMF of 18 volts, and it's connected to 3 resistors, okay? So resistor 1 is in series with a parallel combination of resistor 2 and resistor 3, okay? So the first thing you're going to want to do when you're solving these circuits is you want to find the equivalent resistance. And when you find the equivalent resistance, you're going to want to draw each kind of intermediary circuit, okay? So this is what I mean by that. Let's find the equivalent resistance of those 3 resistors. So we first locate the region with the highest concentration of resistors that are in the same, that are either in parallel or in series. And here we have R2 and R3 in parallel. So we're going to tackle those 2 first, okay? So R2 is in parallel to R3. And that means that the equivalent resistor, which I'll call R23, is going to be equal to R2 over R3, 1 over R2 plus 1 over R3. And so therefore R23 is going to equal 1 over 6 plus 1 over 3 to the negative 1. Make that better. Okay, so 1 over 6 plus 1 over 3 ends up being 3 over 6. And inverse that, that equals 2 ohms. All right, so let's draw that circuit. I'll call this kind of circuit 1. All right, this will be OG circuit. So circuit 1 is going to look like this. It's going to be 2 resistors in series, right? Where this is R1 and this is R23. So let's keep going. So let's further refine this circuit number 1 into 1 equivalent resistor. So we have 2 resistors in series. So I'm going to have equivalent resistor 1, 2, 3 is just going to be equal to R1 plus R2, 3. And that's going to be 4 ohms plus 2 ohms, just 6 ohms. And let's draw that. So this is kind of circuit number 2. And that's just one resistor and one battery where the value of that resistor is R1, 2, 3, 6 ohms, right? So I did that. So now what? Well, let's look at the question. What did the question want? Find the current in each resistor. Okay, we're going to find the current in each resistor. So I think it's going to be easiest to first find the current through the equivalent resistor, R1, 2, 3. Okay, right? Because there's only one resistor, and we know that V equals IR. Okay, so the voltage across 1, 2, 3, well, that's just going to be equal to the voltage of the battery. And that's going to be equal to the current through 1, 2, 3 times R1, 2, 3, which is 6 ohms. So therefore, the current through that equivalent resistor R1, 2, 3 is going to be 18 divided by 6, which is 3 amps. So we have 3 amps of current running through this circuit right here. Well, if we take that information and apply it to circuit 1, that means that we have 3 amps running through R1 and R2, 3 because R1 and R2, 3 are in series, right? And as we saw up here for resistors in series, the current is constant, okay? So that means we can figure out that the current through R1 is 3 amps. So we have one answer. And so now it's time to figure out what's the current through R2 and R3, okay? Well, what we know is that the current entering this junction C is 3 amps, and the current leaving junction B is 3 amps. So this 3 amps is going to be split up between R2 and R3. So a portion of the 3 amps is going to flow through R2, and a portion of the 3 amps is going to flow through R3. So how do we figure out how much? So let's look back at our rules for parallel circuits. If we want to find the current through resistors in parallel, we need to use the potential that's equal across each resistor and divide it by the resistance value of that particular resistor, and that will give us I1 and I2. So the question is, well, we don't really have all that information, right? Let's kind of write what that is. So I1 is going to be the voltage across, no, we need I2 and I3. I2 is equal to the voltage across R2 divided by R2. I3 is equal to the voltage across R3 divided by R3. But we know this, but we don't know the voltage across R2 and R3. So we need to find that missing piece of information in order to figure out what I2 and I3 is. So let's look at our rules for potential. So our rules for potential in series. Okay, let's look at circuit number 1 again. So if the potential of this battery up here is 18 volts, well then the potential of R1 plus the potential of R2, 3 must equal 18 volts, okay? And well, we kind of know, we have all the information that to be able to find what VR1 is, right? Because we know what R1 is and we know what I1 is. So we can solve for what VR2, 3 is. VR1 is I, which was 3 amps, times R1, which is 4 ohms. So VR1 is 12 volts. That makes VR2, 3, 18 minus 12, minus 12 volts, 18 minus 12 volts is 6 volts. So the voltage across 2, 3 is 6 volts, which means the voltage across R2 is 6 volts, and the voltage across R3 is also 6 volts, right? Because they're in parallel. And remember, parallel circuits, the voltages are all equal, okay? So now that I know that the voltage is 6, I can plug that into my equations for the current through each resistor. I have 6 volts over R2, which is 6 ohms. And then I have 6 volts through R3, which is 3 ohms. So that makes my I2 1 ohm and my I3 1 amp and my I3 2 amps, okay? And sure enough, adding them together gives me back that 3 amps, which is what I have coming out of junction B, right? So it all makes sense. So we figured out the current through each resistor, okay? And we did that by applying these rules above here, okay? The rules for resistors in series and in parallel. And I'm going to tell you these rules are actually just specific formulations of Kirchhoff's rules, okay? So I'm going to tell you another set of rules, and then I'll go back to these examples and talk about them, okay? I'm going to tell you another set of rules, and I want you to see how applying those two resistors in series and parallel gives you those set of rules that we just talked about, okay? So Kirchhoff's rules basically are used to analyze networks, of resistors and batteries and capacitors, okay? And the first rule is called Kirchhoff's junction rule. And remember, a junction is a point where the current kind of splits and, right, it has a decision on where to go. So Kirchhoff's junction rule states that at any junction, okay, at any point where we have these currents splitting or joining together, the sum of all the currents in that junction must equal 0, okay? So if I have current coming from the left, right, into the junction, I have current coming from the right into that junction, all my N2s, right, should equal all of my outs. So that if you add them all together, it equals 0, right? Right, if I move all that over, all my N2s and all my outs should add together to equal 0. And you can think of it kind of as like a water pipe analogy. So if I have water going into a junction, right, all that water that I have sent into the junction must be add to the water leaving, right? Or else there's nowhere else for the water to go. So the same thing for the current. There's nowhere else for the current to go. And so this Kirchhoff's junction rule, this is a statement in the parallel. Let's go back to the parallel, right? So that's basically this statement right here. Oops, didn't mean to erase that. Is all the currents coming into a junction, okay, this I must equal I1 plus I2 plus I3. Okay, this I here must equal I1 plus I2 plus I3, right? I is going into the junction. I1 is leaving the junction. I2 is leaving the junction. I3 is leaving the junction, right? So, and what is current I? That's the current through the equivalent resistor of R123, okay? And so if I were to add them all together, add all my ins and add all my outs, right? If I subtract that, I would get 0. So these rules for current and voltage and resistors in parallel, this is just a formulation of Kirchhoff's junction rule. And so there's one more Kirchhoff's rule, that's the loop rule, okay? So the loop rule states that in any closed conducting path, all the voltages must equal 0, okay? And we actually just looked at this loop rule. I didn't exactly tell you what it was, but at the very end of chapter 25, we kind of did that. We did the loop rule. So let me scroll back and show you that picture here. Let's go back to chapter 25, the very end. Right here, right? We saw that we added up basically, right, the positive potential we got from the battery, subtracted by the potential that we lost going through the internal resistor, subtracted by the potential we lost by going through a resistor of 4 ohms, right? All that equaled 0, meaning we were right back where we left off, right? We started off at 0, we crossed the battery, got potential, lost potential back to 0, okay? So this picture is a statement of Kirchhoff's loop rule. So the loop rule is a good rule to apply. So applying the loop rule is basically a statement that the electrostatic force is conservative, meaning there is no energy gained or lost, or no potential gained or lost in a circuit, right? It's a closed system. So when we apply the loop rule, there are some conventions we need to consider, okay? So when you apply the loop rule, maybe we should do an example. Let's do this example after I briefly explain these conventions, okay? So when you are looking at a complex circuit and you want to apply the loop rule to give you a set of equations, okay, to help you solve whatever it is you need to solve, you're going to draw a loop, okay? And that loop that you draw is arbitrary. And it's arbitrary because as long as you follow these conventions correctly, you will still arrive at the correct answer. And so this blue arrow, this travel arrow, okay, that's going to be the direction of your loop that you draw in order to keep track of all the potentials changes, okay? So if this loop that you draw crosses the battery from its negative terminal to its positive terminal, another way to think about it is if you are leaving the positive terminal and entering the negative terminal. Okay, there's 2 ways to kind of think about it here. But if it's going in this direction, okay, then anytime you cross the battery, you're going to add potential to the system, okay? And so the counterpoint to that is this right here. So if you are traveling in this direction, you will most likely be traveling right from plus to minus, okay? So that means you're going to be crossing the resistor in this way, leaving the positive terminal, going to the negative terminal, okay? And when you cross the resistor in this way, right, this is the side of the resistor connected to the positive terminal of the battery. This is the negative side of the resistor connected to the negative side of the battery, okay? So when your direction of travel of your loop is going this way, then anytime you cross the resistor, you're going to lose potential, okay? So these go together, right? They're opposites. And so now, well, what happens if you draw your loop the other direction, okay? What happens if you draw your loop so that you're leaving the negative terminal and entering the positive terminal? Well, that's fine. You can do that. It's an arbitrary choice of travel, but when you do, you need to make sure that you're subtracting instead of adding, right? That you're subtracting potential from the system. And when you do that, you're most likely going to end up with crossing a resistor in the opposite direction of the current, right? Because remember, current leaves the positive terminal and goes to the negative. Like that's the definition of I. So if your travel direction is opposite to that current direction that we have defined as positive current, then you're going to be adding potential anytime you cross a resistor. Okay? So think about that. It seems kind of like, okay, I get this, but when you get to a complex circuit, just refer back to this picture, okay? And it's going to help you. And just try to match up what you're doing, okay? And we'll do an example together. So let's look at this example. All right, we have 2 resistors, 2 batteries. And this is a circuit for when you're charging a battery, okay? Using your car's battery to jump or charge another car's battery, all right? So we have the dead battery down here. It only has 4 volts, needs 12. And it has an internal resistance of 4 ohms. And then up here is our live battery. It has an EMF of 12 volts and only 2 ohm internal resistance, okay? And in between, we have some resistors connected to the circuit. And we want to figure out what the current in the circuit is, okay? We want to figure out the potential difference, VAB, and the power output of each battery, okay? So let's do that. Let's apply Kirchhoff's loop rule. Since there's no junctions, right? There's no junctions here, so the current rule, the junction rule isn't really going to help us, right? So we're going to use Kirchhoff's loop rule here since there's no junctions. And when we apply Kirchhoff's loop rule, we're going to choose a direction of travel. So we're going to choose this counterclockwise direction, okay? And when we choose that counterclockwise direction, we're gonna start adding up our potentials. So let's start here at point A, okay? And we're moving in the direction of travel, which happens to be the current direction, and we're gonna encounter a battery. All right, well, first we encounter a 4 ohm resistor. And if we look, here's the resistor's negative side, here's the resistor's positive side. And we're going in the current direction. So if we want to add up all the potentials in the circuit, this one is going to be V of the 4 ohm, okay, plus V of the 4 volt battery, and then we'll get V of the 7 ohm, V of the 12 volt battery, V of the 2 ohm battery or internal resistor, and then finally V of the 3 ohm, right? So now let's figure out, are these all positive or negative? All that should equal 0, right? Because we returned back to point A. So now it's time to apply our positive and negative potentials according to the rules or the sign conventions here from the previous slide. So we have assumed that the current direction is counterclockwise. And then we've also decided to do our loop in the counterclockwise direction. So if our current direction is not correct, well, then our result from applying the loop rule will be negative I. So we'll know that that our current will be going in the opposite direction, okay? But for now, I think that this is a good approximation or a good guess, because if we look at the larger, right, the battery with the larger EMF here, that's going to overcome this battery with a smaller EMF of 4 volts, and the net current should follow the 12 volt battery, right? And the current, as we know, is made up of positive charges, so they would leave the positive terminal and go around and enter in back to the negative terminal. So I think this is going to be a good guess, and we're not going to have a negative I. So if you do encounter in your other homework problems 2 batteries, then I would, for your guess of what direction the current is, you go with the larger of the 2, okay? And the current would, of course, leave the positive terminal and enter the negative terminal. So, all right, so let's go back to what we were saying. Let's find out what's the voltage. If we're starting at point A, what's the voltage due to the 4 ohm internal resistance? Well, we're traveling in the current direction, okay? So if we are traveling in the current direction, then we should be having a negative IR here. So negative I times 4 ohms, okay? Now, what about crossing this battery? Well, our travel direction is going from that positive terminal to the negative terminal, okay? So if we are going from the positive terminal to the negative terminal, we will be subtracting E, okay, right? If we're going from the positive terminal to the negative terminal like this, that would be minus E, so that's minus 4 volts. Minus I. No, it's minus 4 volts. Right, we don't need I times R because it's the battery. And so now let's look at the 7 ohm resistor. So our current is in the direction of our travel. So for a resistor, when the travel direction is in the direction of the current, you do minus IR. So that's minus I times 7 ohms. And then we encounter this battery. So now the battery, if you notice, the terminals are linked up, right? Minus on this side to minus on this side. So now when we travel across that battery, we're going from minus to plus. And so when we go from minus to plus, right here, minus to plus, that's our direction of travel, we're going to add the 12 volts. Now we're going to cross the 2 ohm resistor. That's going to be, right, and our current is in the direction of travel, so that's going to be minus I times 2 ohms. And then finally, the 3 ohm resistor, that's going to also be minus I times 3 ohms, okay? Because our current direction is in the direction of travel. And so all that's going to equal 0. So let's mathematically, collect everything together. So we have a 12 volt here. We have a minus 4 volt here. So that's going to add up to 8 volts. When we move it to the right side of the equation, that'll be negative 8 volts, okay? And then we add up our i's, so we have minus 4i, minus 7i, minus 2i, minus 3i. So that's 5, plus 4 is 9, plus 7 is 16. So we have a minus 16 ohms times I. And so when we solve for I now, we get I equals negative 8 volts over negative 16 ohms. And sure enough, that is 0.5 amps. Okay, so that's our current through the entire circuit. All right, and why? Because everything's in parallel. So the current through the whole circuit is going to be the current through each individual element. Okay, so here's I. I is 5.5 amps. And so now we want to find the potential difference VAB. Okay, so we want to find the potential difference between point A and point B. And so what we can do is we can add up all the potentials in between those. So we can either add them all up on this side or add them up all on this side and find out what that potential is. So if we start at point A and go to point B, it ends after the 7 volts. So that's basically, after the 7 ohms. So that's basically this stuff right here. Okay, so VAB is going to equal, and I was 0.5, right? So negative 0.5 amps times 4 ohms minus 4 volts minus 0.5 times 7. Okay, so that equals negative 2 volts minus 4 volts minus 3.5 volts. So that's 9.5 volts. Okay. So the potential difference is 9.5 volts. And then the power, we didn't talk about what power is, but power is IV. Okay. So I'm not, really covering, we just don't have time to cover every section of every chapter. So don't worry too much about power, but just for the sake of completing this example, P is IV, right? Current through the battery times the voltage of the battery. So the power then, since the current is 0.5 amps, the power through the first battery, the 4 volt battery, would be 0.5 times 4 volts, 2 watts. 2 watts. The power through the 12 volt battery, 6 watts. Okay, so this example is just basically to illustrate how to use those sign conventions when using Kirchhoff's loop rule. All right, so crossing the batteries was really the most difficult part because, you know, one battery, right, has, if you kind of look, it looks like they're in the same polarity, but they're really in opposite polarity because the negative side is connected to the negative side here, right? If they were in the same polarity, you would have plus minus, plus minus. Okay, that's two batteries connected with the same polarity. But what we have in this situation, and when they're in a loop, it's hard to tell, right? What we had in this situation was plus minus minus plus. So when you cross one should be positive, and when you cross the other, one should be negative. Okay, so that's kind of the tricky part here. So with that, I want to leave you guys to do these examples since I'm not going to be testing on these. I want to get to the final part of chapter 26 that will be on the exam, and that's RC circuits. The final topic that we'll cover in chapter 26 is RC circuits. So we're going to examine specifically the time dependence of a circuit that contains both a resistor and a capacitor in series, okay? So the time dependence here is going to be really what we're focusing on. And so to start off, we're going to start off with the resistor and a capacitor in series. Okay, they're going to be connected to a battery, and we're going to idealize this battery to have no internal resistance, okay? And we're going to ignore any resistance due to connecting, you know, the wires, right? And we're going to begin with an initially uncharged capacitor. And so with this switch open, we're basically controlling when we begin charging the capacitor, okay? And so with the switch open, recall that open circuits have no current flow, right? So with this switch being open, we are not allowing any charging or any current to flow. And so therefore we can control when the charging begins. So we let some initial time, t equals 0, be the time that when we close the switch, the circuit is complete, and we're allowing the current to move around the loop and begin charging the capacitor. So when we close that switch, there is a current flow, and that current moves around the circuit and begins depositing charge on those two conducting plates, all right? And so what we're going to monitor or, you know, write down mathematically is how the charge increases on those plates as a function of time. It turns out that it's an exponential function, okay? So the charge on that capacitor in the RC circuit, it increases with an exponential function. And here is the form of that function, okay? So the charge at any time t, so another way to write this Q would be Q at any time t, right? That's going to track the charge on the capacitor, okay? And at t equals 0, okay, we should have no charge on the capacitor, right? So what happens when you plug in a 0 here? Oh, my pencil died, of course. So when you plug in a 0 for t, you get e to the 0, which is 1. And then in the parentheses, you have 1 minus 1, which is 0, right? So we definitely get back the fact that at t equals 0, there is no charge in the capacitor. And so as t begins to increase, you're subtracting a number from 1. And that number is becoming less and less than 1, right? So you're getting more of that initial CE charge, or I should say final capacitance charge back, right? So as t gets bigger, e to the negative t over RC gets smaller, and we're subtracting that small number from 1, and eventually that number is going to be so small that all we're going to have left is just CE times 1, okay? So what's the CE thing? Well, that is the final charge of the capacitance, okay? And where do we get that from? Well, we get that from our equation for capacitance, right, which is C equals Q over V. So if we solve that for Q, well, that's just CV. And what's V? V is the potential across the capacitor. And since it's in series with a battery with EMF epsilon, right, V is simply epsilon. So this is how we charge a capacitor, right? This is the model that we use for charging a capacitor. And so what's RC then, right? This constant underneath the T. Well, that's the time constant, right? That's the resistance of the resistor times the capacitance of the capacitor. And that is the time constant of this exponential function, okay? So when T equals RC, we get a value of final capacitance divided by E, okay, which is a characteristic time of an exponential function. So what happens, so we looked at the charge, right? So what happens to the current in that circuit as a function of time, okay? While the capacitor is charging, right, there's a finite current running through this circuit. So every charge that gets donated out of that current to the capacitor, well, that reduces the current a little bit, right? So the current should decrease exponentially as we charge a capacitor because it's constantly donating charge to the capacitor. And eventually that current should reach, back down to zero, okay? So we can track now the current, which we do realize, right? Current is charge, rate of charge with respect to time. And if we take the derivative of this function up here, we get the following function down here, okay? Where the current at any time t in a charging circuit, okay, is the EMF's battery, the battery of the EMF divided by the resistor times e to the negative t over RC, all right? And well, what's that E over R? That's simply the initial current in the circuit, all right? V equals IR. So remember, epsilon is simply a potential V, okay? So, and certainly as you increase t, you can see how e to the minus t would decrease eventually to zero, right? That's how exponential functions work. So these two equations describe the charge and the current through a capacitor, okay? As we're charging the capacitor. So now let's look at the time dependence of a capacitor as it's discharging. And in order to discharge a capacitor, we need to remove the battery, or else the battery would just keep recharging the capacitor and we would never see the discharge behavior of the capacitor. So we remove the battery and we start off with the capacitor initially charged to its fullest amount, Q naught, okay? And the switch is open to prevent the current from flowing. So we close the switch and current begins to flow. And as t increases, as the time increases, the magnitude of this current decreases as well, and so does the charge on the capacitor. So why is that? What's happening? Well, the potential on a capacitor, right, we can figure out by the capacitance relationship. So the potential across a capacitor is Q over C, okay? And as soon as you close this switch, this capacitor behaves as a battery with potential V. But as the switch is closed and time is allowed to progress, we begin losing Q, right? So as Q decreases, so does that battery's potential, right? And if that battery's potential is decreasing, then so does the current in that circuit, right? So in a discharging circuit, a discharging capacitor circuit, both the current and the capacitance, the charge on the capacitor decrease, okay? So, and how do they decrease? Well, they decrease also exponentially, all right? So the charge at any time t on a decreasing discharging capacitor starts off with its maximal charge, Q naught, and decreases by an exponential function, e to the negative t over RC, right? Which is definitely this graph right here. What about the current? Well, the current's a little bit more confusing. That's because the direction of the current is actually opposite to what was shown in that figure. But, right, opposite direction of current, that just puts a negative sign in front of the current. The fact of the matter is that the magnitude of the current is still decreasing, okay? Right? The magnitude of the current is still decreasing with time. And so it also is going to follow an exponential function, right? E to the minus t over RC. But it's going to be scaled by negative Q over RC, okay, where Q is the initial capacitor charge. And this negative Q over RC, that's just the initial current in the capacitor, okay? So we've kind of looked at the characteristics of a charging and discharging RC circuit, right? In a charging RC circuit, the current decreases and the charge increases, okay? In a discharging capacitor circuit, the charge decreases and the current decreases, okay? So let's do some examples and apply these equations. So let me go back up to actually example 26.12, charging a capacitor, right? So we're going to use the charging equations. So we have a 10 mega ohm resistor in series with a 1 microfarad capacitor and then a battery with an EMF of 12, okay? Okay, this is 1 microfarad and this is 10 mega ohms. The questions are, what is the time constant T, okay, or not T, tau. Tau is RC. What is the fraction of the final charge on the capacitor at, missing something here. I'll have to tell you what that is. And what fraction of the initial current is still flowing at some time? It looks like I forgot to copy and paste the time there. The time is 46 seconds. So part A, we want to know what the time constant is, tau, and that's simply equal to R times C. Okay, so 10 mega ohms times the capacitance of 1 microfarad. All right, the 10 to the plus 6 and the minus 6 go away, and the time constant is simply equal to 10 seconds, okay? So at a time of 10 seconds, the fraction of the charge has been reduced by a factor of 1 over E. Okay, that's the definition of a time constant. I know the question didn't ask that, I'm just telling you that, right? So Q over Q initial at T equals RC is equal to 1 over E. That's the definition of what a time constant is. So using that kind of same idea, what fraction of the final charge QF is on the capacitor at a time of 46 seconds? Okay, so we need to get the model of a charging capacitor. So that's Q equals QF 1 minus e to the minus tau over RC. So Q at any time t is equal to the final charge 1 minus e to the negative t over RC. All right, so what we want to know is what fraction, so at t equals 46 seconds, what fraction of the final charge gives us, or it is at 46 seconds, right? So we're going to put 46 seconds for t. Okay, RC is 10. We just figured that out, right? And we're going to figure out what this fraction is. So we need to do 1 minus e to the negative 46 over 10, which is to the negative 4.6. Okay, so 1 minus e to the negative 4.6 gives us 0.99. So that's the fraction left. About 99% is left. Or is on, not left, but there's 99% of the total amount. It's almost charged, right? Basically, that's what it's saying. We're almost 100% charged at 46 seconds. So part C is what fraction of the initial current is still flowing? Okay, so, well, the current is given at any time t is given by I naught e to the minus t over RC. So part C is asking us, what is I over I naught at t equals 46 seconds? Well, I over I naught is e to the minus 4.6. And that gives us 0.01. So about 1% of the current is flowing at t equals 46 seconds. Okay? Nothing too crazy here, right? This is exponentially easier than a lot of the complex circuit problems that you'll encounter in the homework. Okay, so that's why I'm putting this on the exam and not complex circuits, because those just take too much time, right? So let's do now the discharging capacitor problem here. Okay, so we're going to use the same resistor and capacitor. So that was 10 mega ohms for the resistor. And that was 1 microfarad for the capacitor. And the question is, at what time will the charge be 50 microcoulombs? Oh, and the initial charge is 5 microcoulombs. So at what time will the charge be 0.5 microcoulombs? And then what is the current at this time? Okay, so we're basically solving for time now, and we're going to use our discharging capacitance or discharging charge equations. So Q as a function of time is equal to Q naught e to the minus t over RC. Okay, and we need to solve for time. So we want to know at what time will we have 0.5 microcoulombs if the initial is 5. And that RC was 10 seconds, right? That we remember from the previous example. So 0.5 over 5 is 0.1. And that's going to be equal to e to the minus t over 10 seconds. So to unlock that, we take the natural log of both sides. Okay, the natural log of a decimal is, or of a number less than 1, I should say, is negative, right? Remember those natural log rules. So this is negative 2.3 is negative t over, oh, I don't know why I wrote RC again. That's 10 seconds. So we're going to multiply by 10 and drop my negatives. So t is 23 seconds. And part B is what is the current at this time? Okay, so the current then, we plug in t equals 23 seconds right there. So our current, we need to know our initial current though, which is charge divided by RC, okay? So for part B, what is the current at this time? So I at 23 seconds will be equal to the initial charge, 5 microcoulombs, divided by RC, which was 10 seconds, right? Coulombs per second. That's our initial current. E to the minus T over RC. T is 23. RC is 10 seconds. All right. So let's find out what I is. So we have 5 times 10 to the minus 7, because I divided by 10, times e to the negative 2.3. And we get a very small current of about, count my decimals here, 1, 2, 3, 4, 5, 6, 7, 8. 5.08 times 10 to the minus 8 amps, right? Coulombs per second. And that's negative, right? Because we define this current to be negative. So, and that's just indicating the direction of the current. It's going to be opposite than the direction of the charging current, okay? So we just put a negative there. And the negative would come from employing this negative right here, okay? Which I didn't do. Should have done it right there. Boop. So not too bad. And I just want to, in case you've encountered this question in the pre-lecture, right? The trickiness of these questions comes from interpreting what the question is asking. And so there will be some questions that will say, what is, how much charge is left? Let me just write it right here. So how much charge is left? Or let me think of how it was phrased. How much charge remains after, 80% is lost, okay? So you might be inclined to put 80% in your equation, but in reality, right, what is Q of T tracking? How much charge is there, right? Not how much is lost, but how much is there. So if you're told how much is lost, you need to interpret that and turn that into how much is there. So if 80% is lost, then how much is there is 20%. Okay? So that's my clue to you. I've had a couple questions about that. So the trickiness of these questions is not in the math and not in which equation to apply. That's quite easy. But the trickiness will come from interpreting and comprehending what the question is asking you. Okay? And there's tricky things like this. All right? So that's what you need to know for the exam. These are some kind of fun things that just, being a human being that lives in a modern home running electricity, these are some interesting things that you should know about your home that you're living in. And so your home is powered by really high amperage, lines coming from your power lines on the street. Okay, and when you have, really high amperage lines, the amps are what's really dangerous to you, right? It's a bunch of coulombs per second. So if you touch something with a high amperage, you are allowing many billions and trillions of electrons to flow through you every second. And they're going to blow through your cells like it's nothing, okay? And so in order to prevent that from happening, fuses are installed, okay, in various parts of your home. You may have an outlet that's called a GFI that buzzes sometimes, and there's buttons that you need to press to keep it from sounding weird. And typically they're installed in areas where there's water, so there'll be a GFI outlet by your sink, by your kitchen sink, okay, in your laundry room. They have these things called fuses, and these fuses contain, a conductor, okay, that's very thin, and it's so thin that if a very large surge of current were to flow through it, it would break this, okay? It would be so hot that it would melt the metal right there, and this fuse would be blown, right? And if there is no connection here, then there is no way for more current to flow. So it's a way to prevent current, really high amounts of current, from reaching a place it shouldn't go, like your body, okay? Or like to a puddle of water that you are touching. So these fuses are, look, there's many different kinds of fuses, and there's some in your car. They're everywhere, okay? And that's their purpose, right? They break when a large amount of current flows through them so that it prevents any more current from flowing and potentially reaching a human being. So circuit breakers are a device that function very similar to a fuse, but they just work a little differently. And they flip when a large amount of current has reached them, right? And that's to protect that large amount of current from continuing to flow and damage whatever's on the other side, okay? So circuit breakers will trip or flip when there is a high surge of current, and that basically breaks open the circuit so that no current can flow, right? It opens the circuit. So the great thing about circuit breakers is that they can be reset after they're tripped, right? You just flip the switch back, unlike a fuse where if it breaks, you throw it away and you have to put in a new one. Let's talk about three-pronged devices, right? Three-pronged cords. So there's a lot of different devices. Some have 2 prongs, some have 3 prongs. And the reason for a 3-prong is the third prong, well, the first 2, let me tell you what the first 2 do, right? The first 2 are basically the in and the out of your circuit, right? They're what form the complete circuit, right? So if the current comes in on one side, it goes out on the other. That's why you have 2 prongs. So anytime you use a 2-prong, you form a complete circuit. Well, what's a 3-prong? So a 3-prong has the first 2 that allow the current to flow in a complete circuit. And then it has a third bonus one. And the third bonus one is there to catch any current that may hop off of the circuit for whatever reason, okay? Something inside breaks, it touches water, okay? There could be many reasons that cause a break in the circuit, and that high amount of current is gonna look for somewhere to go. And instead of going to your hand, which is holding the device, it's going to go to the third prong, okay, which is a metal of low resistance, hopefully lower resistance than your hand. It's going to attract that current to jump into the third prong and safely exit the area, okay, so that it doesn't hit you. So these are some of the safety features in your home or in your devices that you use that are to keep you safe from being shocked by high amperage, okay? So, and they are based on these principles that you're learning in this chapter. So I thought you might find that interesting. So this concludes chapter 26. We're going to take our exam, and then we're going to start a brand new unit that I really love. It's magnetism, and we're going to see where magnetism and where magnets come from. Okay? Good luck on the exam.